small. Now, we can always use the angular frequency. Omega is equal to 2 pi times frequency, nu. And if we use 2 pi, we can always write h bar. Again, we call it Planck's constant, which is Planck constant over 2 pi. So it is a modified Planck's constant or a reduced Planck's constant. So if I use omega, the angular frequency, which is 2 pi nu, where nu is the linear frequency, and if I use the reduced Planck's constant h bar, then this h nu can be written, the energy again can be written as the reduced Planck's constant times the angular frequency omega. So the energy of the photon is simply Planck's constant times omega. And this Planck's constant, which is the reduced one here, is h over 2 pi and omega is 2 pi mu. Okay, this Planck's constant is given this name because of this scientist who came up with the idea that we can think of magnetic radiation, electromagnetic radiation as particles. We also know from the wave properties of electromagnetic radiation, the electromagnetic radiation always propagates as a wave with a velocity c, which is the velocity of light. Light is part of the electromagnetic radiation, and it has a velocity, and the velocity of light, or the speed of light, is 3 times 10 to 8 meters per second. This is a huge, huge speed. 3 times 10 to 8 meters per second. Always the wavelength and the frequency of electromagnetic radiation, the product of the wavelength and the frequency is equal to the speed of light. This is always the case. Okay, so if that's the case, then instead of writing the energy in terms of nu, we can use nu as a c over lambda, and then put nu here, E is equal to h times c over lambda. So that's an alternative form for the energy of the photon. Okay, so let me clean up all this mess maybe, and then just clean it up and see. If we try to clean it up, all of this, so what's important? What do we come up with? What we come up with is that we can look at electromagnetic radiation as waves, and if we look at them as waves, they always move with a speed c, such that the wavelength times the frequency is equal to c. So the electromagnetic radiation, this is a wave like this, and lambda is the distance between two maxima. This is lambda, which is called the wavelength, and the frequency is the time taken to make a full oscillation. All these are related by c equals lambda times v for a wave. Also, we can think of electromagnetic radiation as particles, okay, moving. So many of these particles, each one of these particles is called photons, a photon, and the energy of the photon is equal to h, Planck's constant, times nu, or reduced Planck constant, h reduced times omega, or h c over lambda. All of these give us the energy of the photon. So this is dual nature for electromagnetic radiation. It can be looked at as waves and it could be looked at as particles. Now, so E is h nu and E is h bar omega, and h bar is h by 2 pi. I'm just, these symbols do not show up here, okay? And omega is equal to 2 pi nu, as we said before, and c, the speed of light, or the speed of electromagnetic radiation, is lambda nu. So c is the speed of light, h is Planck's constant, and h bar is reduced Planck's constant, and we can also write the energy of the photon is EHC over lambda. So this is a summary. Now, the photon is a particle, is an object, but it has a zero rest mass. A zero rest mass, that means if the photon is not moving, it has a zero mass. It doesn't exist. It has to be always moving. But electromagnetic radiation is always moving. So that means the photon is always moving. Otherwise, if photon is at rest, it has a zero mass. Okay? So the energy of the photon is entirely kinetic. It has to move all the time. So it's kinetic, it's moving all the time. Each photon has a momentum p, and this momentum p of the photon is the total energy because it has no mass. So we cannot write p, no rest mass, so we cannot write p as mv. This is classical mechanics. It wouldn't work for us here, because photons are, again, very, very small particles that move with a very, very large speed. So it doesn't work, for momentum to be written in terms of the classical momentum. So what we actually use here is what they call relativistic, because the speeds are very high, definition of momentum, which is the energy divided by the speed, c. Okay, which is actually the speed of the photon, because it's the speed of electromagnetic radiation, which is h bar 2 pi over lambda. Okay, h 2 pi over lambda. Why? Because energy is h c over lambda. That's the energy. Okay, and c is lambda nu. Okay, so you can use this and you can immediately see that this is true here. Okay, so the momentum is h bar k, where actually k, this is k here, k is equal to 2 pi by lambda. So the momentum is equal to h bar k. The intensity of the radiation will be proportional to the number of photons. So if you have photons like this making the electromagnetic radiation, and they're incident on some screen, right? So the energy incident on this screen here per unit area is the total number of photons, the energy of the total photons that are hitting this unit area per unit time. So the total intensity is the energy of the photon, one photon, times the number of photons hitting a unit area per unit time. This gives you the energy intensity. Okay, what's the electromagnetic spectrum? What's the electromagnetic wave spectrum. What do we have? We have different types of waves. So this is the electromagnetic wave spectrum. We have radio waves. These radio waves, so it is, electromagnetic waves are waves, and we have lambda here, which is the wavelength, and so this is lambda, and then we have the frequency, which is the frequency of oscillation. Also, the electromagnetic radiation is photons, okay, that are moving in this direction, and the energy of the photon is h nu, or if you like, h c over lambda, either way. Okay. Now, radio waves, the waves with which we listen to radio waves are 100-kilometer wavelengths. So this wavelength is 100 kilometers. Very, very long wavelengths. Therefore, the frequency is very small. And if you multiply 100 times 3, 100 kilometers, so you get C equals 100 kilometers, so it's 100 times 10 to 5. That's lambda. Okay, that's my lambda. Now, times the frequency, which is 3 times 10 to 3. So that's my frequency. And so I get the speed, which is equal to 3 times 10 to 8 meters per second, which is the speed of light. Okay? So for these radio waves, which are very huge, large waves, even larger than the sea waves or the ocean waves, the frequency is 3 times 10 to 3 hertz. Hertz is the same as second minus 1, or per second. We call it hertz. What's the energy of the photon? The energy of the photon is going to be h, which is 6.626 times 10 to minus 34. Okay? Joule times, so this is h. Now I'm looking at the energy of the photon here. This is h times the frequency, which is 3 times 10 to power 3. So this is roughly about, 3162. So this is roughly about 2 times 10 to minus 31 joule. So the energy of the photon is very small. So it's 2 times 10 to minus 31 joule. It's a very small energy. Let us think of another energy. So I tried to do some calculation here, and I tried to show you the energy of the photon, which turned out to be 2 times 10 to minus 31 joule. Now, the question becomes, can we come up with a smaller unit of energy? Joule is clearly a very large unit of energy for these kind of energies that we're talking about. Now, let us think of a potential between 2 points, and let us have a potential difference of 1 volt. Okay, so we have plus, minus, potential difference of . So let us think of a potential difference of 1 volt, and let us have an electron, 1 electron here. So when this one electron sees this potential difference, it will move from the negative plate to the positive plate. And as it moves from this point to this point on this potential of 1 volt, the energy acquired by the electron would be 1.6 times 10 to minus 19 coulomb, which is the charge, okay, times 1 volt. So this energy would be 1.6 times 10 to minus 19 joule. Okay? Because the energy when a charge moves in a potential is equal to the charge times the potential. So the energy for the electron when it moves from here to here at this potential difference of 1 volt, the energy gained is 1.6 times 10 to minus 9 joule. Now, let us call this energy, because it's an energy of 1 electron in 1 electron volt, in 1 volt difference, let's call it 1 electron volt. So 1.6 times 10 to minus 9 joule is 1 electron volt. So this electron volt unit is 1.6 times 10 to minus 19 of a joule. It's a very small unit. So if I divide this here by 1.6 times 10 to minus 19, then what I get is I will get this photon energy in electron volts, and this is what I get. 1.2 times 10 to minus 11 electron volts. So you see the energy is electron volts. And this would be the unit of energy we're going to use throughout this course, because we're dealing with very small particles, with very small energies. We cannot work with joules. Joules are too large, too big. So we're going to work with electron volts. And electron volts is a smaller unit of energy, which is 1.6 times 10 to minus 19 of a joule. So again, let me clean up now that we've spent time discussing all this and explaining what we mean by electron volt. So if we clean up, I don't know whether we've cleaned up much here, yeah? And now what we have, we go back, this is radio waves, then you have microwaves, you get a smaller wavelength, but then you have large frequency. Why? Because always C is lambda times nu. So if lambda goes down, nu goes up, because this stays the same value, right? So you have 300 millimeters for the microwaves down to 0.3 millimeters from radio waves. So microwaves, the range is all of this, radio waves. Microwaves, this is the range from 300 millimeter to 0.3 millimeter wavelengths, and frequency from 1 times 10 to 9 to 1 times 10 to 12. Then you get infrared. Infrared is the heat waves. Okay? And in infrared, it goes from wavelengths of 0.3 millimeters to 0.7 micrometers. 1 micrometer is actually equal to 10 to minus 6 of a meter. So it's 10 to minus 6 of a meter. Okay, that's the infrared. Then the visible light. The light that we see, the red light, the blue light, the violet light, the green light. Micrometer is actually equal to 10 to minus 6 of a meter. So it's 10 to minus 6 of a meter. Okay, that's the infrared. Then the visible light, the light that we see, the red light, the blue light, the violet light, the green light, they are all in the range of 0.7 micrometer down to 0.4 micrometer. And look at the frequencies, 4.3 times 10 to 14 to 7.5 times 10 to 14 hertz. So as we go down, lambda decreases, but the energy of the photon increases. Look, the energy goes up 3.1 as we go to visible light. Then as we go to ultraviolet, okay, then lambda goes down, the frequency increases 7.5 times 10 to 14 to 10 to 16, and also the energy of the photon increases 40 electron volts. And then X-rays, 30 nanometer. So 1 nanometer, which is, again, here we get into the nanoscale. 1 nanometer is 10 to minus 9 of a millimeter, of a meter. So 10 to minus 9 of a meter, that's the nanoscale. Okay? And now in electronics, we're in the nanoscale. In solid state, electronics were in the nanoscale. And that is where the nanotechnology comes in. So X-rays, lambda at the nanoscale. And look at the frequency, becomes huge. But then also look at the energy, electron volts, it's 4 orders, or actually 15 orders of magnitude compared to the energy in the radio waves. And then if we go to the gamma rays, then we get to the pico. 1 picometer, okay, is actually 10 to minus 12 of a meter. So the wavelengths becomes really small, but look at the frequency range, 10 to 18 to 10 to 20. Now look at the energy of the photon. That is why as you go up in frequency, you go up in energy, and then what you have is you have very energetic photons. Here is an example problem. That is, if the minimum frequency photon needed to separate a diatomic molecule is 8 times 10 to 14 hertz, what is its binding energy? So you have a diatomic molecule. So you have 2 atoms, and they're bonded with some covalent bonding maybe, or ionic bond, okay? And what you have is you have incident wave, electromagnetic wave, and it strikes this bond and it breaks it. So what happened is you get the 2 atoms separated now. Each one goes in a different direction because this bond is broken. How is it broken? It's broken by an incident photon. This photon, when it hits the bond has maybe two electrons. Okay, so the photon hits the bond. Okay, the 2 electrons are no longer bonded. It breaks the bond. How does it break the bond? Actually, photon, when it interacts with any body, with any object, it is completely annihilated. It is completely finished. So all its energy, the energy of the photon is EH mu. So it is H here, 6.6 times 6.626 times 10 to minus 34 joule second, times the frequency, that's the photon frequency. This gives you the energy of the photon, E, which is 5.3 times 10 to minus 19 joule. So this should be the binding energy, because all this energy in the photon is given to the molecule to break it off. Okay? In fact, if you divide this by 1.6 times 10 to minus 19, okay, which is one electron, which the electron volt joule relationship, you probably get something like 3, the order of 3 electron volts. So the energy, the binding energy of this molecule is about 3 electron volts. And then find the maximum wavelengths of the photon that will separate a molecule whose binding energy is 20 electron volts. Now we have another molecule and the binding energy is 20 electron volts. What kind of photon energy do we need to separate it? So 1 electron volt is equal to 1 times 1.6 times 10 to minus 19. So it's equal to 1.6 times 10 to minus 19 joule. So 20 electron volts times 1.6 times 10 to minus 19 is equal to, remember, the energy of the photon is hc over lambda, and lambda in the denominator. So we want this energy of the binding energy of the molecule to be separated by a photon, and we want the maximum lambda for this photon. So we want lambda max, which is the maximum lambda. So from this equation here, we get lambda max equal to 6.21 times 10 to minus 8 meters. Look, this is written as 6 to 1 angstrom. 1 angstrom, angstrom is a very small unit. 1 angstrom is 1 times 10 to minus 10 meters. So it's actually equals 1 nanometer. So in this terms of this small unit, angstrom, it is 621 angstrom. That is the wavelength for the electromagnetic radiation that is able, that's the maximum wavelength that's able to separate a molecule whose binding energy is here. So this, where I want to stop today so that you get some time to look at this. But in summary, what we did is we revised classical mechanics. Just broadly told you about different parameters in classical mechanics that we use. But we said that classical mechanics will not be sufficient or will not work satisfactorily for very small bodies. It's perfect, it's okay for large bodies with relatively small velocities. But for small bodies like electrons, like molecules, etc., like photons, that's a new body that we learned in this class, we need another type of mechanics. Now, as an introduction to this new type of mechanics, we started looking at a different perspective for the electromagnetic radiation. We know electromagnetic radiations are waves. We know they have wavelength lambda. We know they have frequency mu. We try to look at electromagnetic radiation as particles. We try to think of them as a shower of particles. Each one of these particles we call photon. It has a zero rest mass, so it has to be moving, or its energy is kinetic. The energy of each individual photon is a constant h, which we call Planck's constant. times the frequency nu of electromagnetic radiation. So electromagnetic radiation has a dual nature, has a nature of it being wave and has a nature of it being particles. So this is where I would like